So
Can you hear me?
we will listen now to Professor Anil Kumar from India. He will speak about the generalization of spin factors. So welcome, Professor, and you can start.
Thank you. I thank the organizers for giving me this opportunity. Let me first share my screen. It's here. So is my screen visible?
Yes, it's okay.
Yeah. Thank you. Yeah. So I thank the organizers formally for inviting me for this conference. I'll be speaking about an order. Actually, the title should have been more appropriate, and order theoretic generalization of spin factors. Actually, what I'll do, we know that spin factors, I will quickly define it. They are actually kind of Jordan algebras, but then it has certain order structure, and which I will be generalizing to in a more general setup. So here is a small plan of the talk. I have divided this in 4 parts. Briefly, I shall introduce spin factors. Then I'll come to the main body of the talk. I'll discuss adjoining of an order unit to a non-linear space. Then after adjoining, we study some order structure. And in the next part, we'll discuss the norm structure briefly. And in the last part, we'll discuss certain spectral property of one of the spaces obtained from the norm structure. So the spin factors. Here, I think I need to confess that I'm not expert in spin factors. It's an object in mostly mathematical physics. So I've just copied few sentences from somewhere here and there. Even in mathematics, you don't see many write-up about spin factors. So let me quickly define what we mean by spin factors. So we go as follows. We begin with a real Hilbert space H and consider a C algebra and assume that we have a map chi from H to A, which is linear and satisfies the 2 conditions, namely the twice of the symmetrized product of the Jordan product of chi xi and chi eta is 0, and the symmetrized product of chi xi with chi eta star results in the inner product xi eta multiplied with the identity operator. If so, a linear map satisfying these 2 conditions is known as canonical anti-commutation relation, or CAR, and they are very important in mathematical physics. How? You will ask me, I'll say no. I don't know, I mean, but I hear that they are very important. So, so what we do next is, now we add chi xi to chi xi star and define a new operator psi at xi, so that we get now isometric linear mapping xi from H into now the self-adjoint part of C algebra A. And this satisfies condition 3, namely the Jordan product or symmetrized product of psi xi with psi eta results in the inner product xi eta multiplied with the identity operator. So it's a kind of, it is taking the product into the inner product if you overlook the identity operator. So now, because we want this multiplication to be in, so we need to include this identity. So what we do, we take the image of H under xi and adjoin identity, then we get actually a unital concrete Jordan algebra in ASA. Even converse Edward converse also holds. Let's go abstractly now. Take H to be any real Hilbert space and define a kind of product, little o product, xi comma alpha with eta comma beta to be this beta xi alpha eta, that is just a cross is a linear multiplication, and in the scalar part we take the inner product of xi eta added with the product of alpha and beta. Then we notice that this space H that some R becomes actually a Jordan algebra obtained. Okay, I'll come to the norm maybe a little later. So, and this is asymmetrically Jordan isomorphic to a JC algebra in some suitable C-star algebra. And such spaces are known as spin factors. But they are called spin factors actually here. They can be generated through something what we call polyspins, which again I'm not very much aware of. I've just heard of and seen them here and there. Okay. So my purpose is to generalize this kind of structure and understand that what makes that generalization what makes that structure a generalization structure, that is under what condition that generalization becomes a spin factor. Okay, so this is my main body of the talk. One more thing I think I should add here is that this talk is more about examples and counterexamples, and then here and there some interesting geometric characterization of non-linear spaces. Okay, so the first part, the beginning. Let's begin with the real non-linear space V. And we consider V dot. This symbol is, this dot is reserved for certain T's that I will insert later. And this is for the general one. So what we consider V dot to be V cross R. And then we define something called V dot plus to be the set of ordered pairs V comma alpha, so that norm of V is less equal to alpha. Then we notice that V dot with V dot plus becomes a real order vector space. And here V dot plus is proper, generating an Archimedean. And then we also get E, which is actually 0, 1, which is a positive element, and this becomes an ordered unit. And V dot with this ordered unit becomes an ordered unit space. And then the corresponding ordered norm you can define as norm V plus mod alpha for any ordered pair V comma alpha. Then yeah, so and this is actually the ordered unit. And not only that, if we now identify V with V comma 0 in this V dot, then this is an asymmetric embedding. Therefore, this becomes a closed subspace. And V dot becomes complete under this norm, the ordinate norm, if and only our given space is complete under the given norm. This structure, this construction looks like a folklore. I don't know which year, but I believe that M.M. Day, Malam Day, I think in 60s, has introduced this structure to generalize Hahn-Banach theorem in order theoretic setup. That is, to prove a positive linear extension on ordered spaces, and through that, just adjoining the ordered unit here, we can get the Hahn-Banach theorem. Okay, now let's see certain elementary properties, and then we move to the next definition. What we notice is that the pair V comma alpha is positive of course, this is our definition that norm of V is equal to alpha, that's alpha is positive number, and norm of V alpha is negative if norm of V is less equal to minus alpha. Eventually, we note that if V alpha is positive, then minus V alpha is also positive. Similarly, if V alpha is negative, then minus V alpha is also negative. And the third situation, which is actually generally a non-trivial situation, that under which condition an ordered pair V alpha is neither positive nor negative, and this is given by that mod alpha should be strictly less than norm V. Okay, I think here I should have commented that the cone obtained here looks like the ice cream cone Johan just mentioned in the last talk. Okay, so here is the following. Now what I do is I introduce something what I call the absolute value of this ordered pair V alpha. And how do I do it? I have three sets of vectors in V dot, and I define mod of V alpha accordingly. If it is positive, I take it as it is. If it is negative, I put a minus sign because I want mod of any vector to be positive. And for the third pair, where it's neither positive nor negative, the definition becomes non-trivial, and we define this to be mod of V alpha, V comma alpha to be mod alpha divided by norm V times V comma norm of V. Then this modulus will be called the absolute value in V. Okay. We can notice the three immediate properties hold just from the definition of the modulus, namely modulus of V is V itself, it is V is positive, that's the definition. Then modulus of V comma alpha plus minus V comma alpha is always positive. And if I multiply V alpha with any real scalar K, then the modulus of K comes out of the modulus. These are three elementary properties. And these three properties now allow us to define something what we call orthogonality. That's going to be the backbone of what we'll be discussing very soon. So now take two ordered pairs U alpha and V beta, and we say that U alpha is orthogonal to V beta, and we write U alpha per V beta if modulus of U alpha minus V beta is U alpha plus V beta. This is our definition, and this is the standard definition in C-star algebras, and even in, you can see in vector lattices. So this is kind of generalization, or this is including both of them. Okay. The first observation we make is that if U alpha is orthogonal to V beta, then U alpha and V beta must be positive. And if any ordered pair is orthogonal to the ordered unit, then the ordered pair is bound to be the zero vector. And similarly, any positive element is always orthogonal to the zero vector. Now in the next result, we can precisely characterize the ordered pair of positive elements. Of course, we assume them to be non-zero. So we take U alpha and V beta to be positive other than zero. And if they are orthogonal, then what we have is that alpha must be norm of U, beta must be norm of V, and the normalized U must be negative of normalized V. Conversely, choose any U in V with norm of U is 1, then alpha U comma alpha is orthogonal to minus beta U comma beta for any alpha and beta positive. So this is kind of if and only conditions. We know the orthogonal pairs precisely, besides zero element, and yeah. So from here we can deduce that if we take three positive elements U alpha, V beta, and W gamma, which are non-zero, such that U alpha is orthogonal to the remaining two, namely U alpha is orthogonal to V beta and U alpha is also orthogonal to W gamma. Then U alpha will be orthogonal to the modulus of B alpha plus W gamma. So in that case, you don't need modulus because they are positive. And it's orthogonal to V beta minus W gamma, but now this time we need to take the modulus. Okay, now comes the thing I would call the backbone of this, and I will tell you why this is backbone. Okay, so first let me state the result. So now again take three vectors, three pairs, U alpha, V beta, and W gamma, positive, non-zero, and assume that U alpha is orthogonal to V beta and W gamma is lesser or equal to V beta. That is something smaller. Then this U alpha is orthogonal to this smaller positive vector order pair if and only if V, the space, our given nonlinear space V must be strictly convex. And what is strict convexity? Just let's quickly recall that if we take two unit vectors V and W in V is not equal to W, the norm of V plus W must be strictly less than 2. And this structure, that is V is strictly convex, precisely shows with this property that if U is orthogonal to V, sorry, U alpha is orthogonal to V beta, then U alpha will be orthogonal to any vector less equal to V beta and positive. Why this is needed and why this is important? Okay, let's come to the next definition and then I'll tell you. So this is the definition I had introduced, I think a few years ago, that take any real ordered vector space U comma U plus and let this modulus be mapped from U to U plus, satisfying the conditions that were mentioned. 1, 2, 3 we saw, fourth we have just seen as a corollary, and fifth is the last result. That is, if U is orthogonal to V and W is less equal to V and positive, then U is also orthogonal to W. Then we call U plus with this modulus as an absolute ordered vector space. Why this property 5 is important is lies in the characterization of orthogonality in C-star algebras. Namely, we know that actually this again I proved in one of the papers. Maybe I will show at the end in the references that if you take two positive operators in C-star algebra A, U and V, then U is algebraically orthogonal to V, that is U into V is 0, if and only if they satisfy this condition. That whenever I take W to be less equal to V and W is positive, then U is also orthogonal to satisfy this condition. So it's a kind of generalization of algebraic orthogonality in the sense of order theory. And that's why I call this setup to be an absolute order vector space. Now, we can summarize what we discussed so far in this section. And we say that V dot with V dot plus and the modulus given in this way is an absolute order space if and only my nonlinear space V is strictly convex. So we can see that except for the last condition, this 1, 2, 3, and 4, the conditions 1 to 4, they hold for any nonlinear space, but for fifth, we need strict convexity, but that is needed if you want to mimic C-star algebra or if you want to include C-star algebras in the setup. Okay. So what we do is now, so we have done all these things. So what we do, we take a non-linear space V, and we consider this space V dot plus, and this modulus, then we'll say that this V dot is obtained by adjoining an order unit to V. So if V is strictly convex or non-linear space, then V dot obtained by adjoining order unit to V becomes an absolute ordered vector space. Now let's quickly come to norm structure. So to define a norm structure, we need to recall few notations. Take U plus and with some norm to be norm ordered linear space. We need order structure as well as the norm structure. They need not be related in the beginning, but at the end we would like them to be related. Okay, so take now two positive elements U and V, and we say that U is absolutely T orthogonal to V, where T lies between 1 and infinity, if for any U1 less equal to V and U1 positive, similarly V1 less equal to V and positive, we have this condition that norm of U1 plus K times norm of V1 is given by this relation when T is finite and greater than equal to 1. And in case of infinity, we take thus the maximum as usual. And this condition actually is known as that U1 is T orthogonal to V1. This notion was introduced again to study the algebraic orthogonality. Okay. And now based on this definition, now we propose the norm to have certain properties, namely we begin with now an absolutely ordered vector space U plus with the modulus, and assume that there is a norm. Oh, it's a typo, it should be U. Then U plus with modulus and norm is said to be absolutely ordered order smooth T norm space. T lies between 1 and infinity, both 1 and infinity included, if they satisfy conditions OT1, per T1 and per T2. OT1 is a kind of it respects order convexity in this way. And then the OT part T1 and part T2 relate the orthogonality with respect to this modulus and this absolute orthogonality with respect to norm. So actually the two things together say that U is orthogonal to V if and only if U is absolutely T orthogonal to V. So in case when we take T to be infinity, then so this will be called absolute order unit space, provided there is an order unit E and the norm is determined by that order unit. Now, we introduce a norm on V dot, where V is a now a strictly convex non-linear space, because I want the fifth condition to be there. That is, it should respect the absolute orthogonality kind of thing. And then we define T norm of V alpha to be this nice quantity modulus of alpha plus norm V raised to power T and modulus of alpha minus mod norm V whole raised to power T whole divided by 2, and then take the Tth root if T is finite and greater than equal to 1. In the case of infinity, we just take the maximum. Okay. Of course, it's very easy to check that this becomes a norm. We just need to use the Minkowski inequality. Then we see that in this T norm, V can be embedded in V dot, and similarly the other component R also can be embedded in V dot. And the third one is not that important, but sometimes is helpful, that norm of V comma norm V in the t sense is 2 raised power 1 minus t multiplied with norm v. So in case of infinity, in case of infinity, we get twice the norm, and in case of t is equal to 1, we get simply the isometry. Okay. So let me just take the result, because I don't have time to prove any one of them, that with this norm T, V dot becomes an absolute order smooth T norm space. Needless to say that the proof runs in with many tricks, in many steps, because you have to isolate. Sometimes t is equal to 1, sometimes t is infinity, and t third case would be t like 1 infinity, and then you have to separate many identity. But anyway, so at the end we get that this becomes an absolute order, and that is why this norm is needed. And one may wonder that what this alpha plus norm v and alpha minus norm v is doing here. I think very soon I will be telling you what are these two quantities related to v alpha. Okay, but okay, so if I take this t norm, then what now I do is simply borrow this t from here and put here, and then omit this t, as we do for LP spaces. So we just put a t here. So Vt, this is the order smooth T norm space adjoining and adjoining an ordinate to V and considering the T norm. So in case when T is equal to infinity, then our definition is that norm of V alpha should be maximum of these two quantities, namely maximum of mod alpha plus norm V and mod of alpha minus norm V. And then this turns out to be our original ordinate norm, namely norm V plus mod alpha. So we can quickly say that if V is a strictly convex real normless linear space, then V infinity is an absolute order unit space corresponding to the order unit E, which is 0, 1. So of course, we have similar situation when t is equal to 1, but I don't think that I'll be discussing that here. I have to discuss something else. Now let's go to something interesting, what we call the spectral properties. What are those? So to define a spectral property, certainly we need to introduce the notion of projections, and this we actually rename as order projections, because they mimic the projections in C-star algebra. Actually, in the C-star algebra sense, this condition precisely gives us the projections. So we call them order projection. So what are order projection? Take any positive element u alpha lying between 0, of course, and the identity that at the unit, that is 0, 1. Then we call u alpha to projection if u alpha is orthogonal to E minus u alpha. And set of order projections in V dot will be denoted by O infinity V dot. In particular here, OP of V dot, and here we will call them, we'll have OP of V infinity that we are more interested in. Okay, but these are the properties which hold without norm, so that's why I kept just dot to tell that no norm is there. Okay, so we know the complete description, because we have the characterization of orthogonality, and that tells us that u comma alpha will be an order projection if norm of u is half and alpha is also half, if the projection is other than 0 and identity. Of course, these are two trivial projections, 0 and order unit, and then others are given by this. So now we know all of them, all the order projections in V dot. So a quick corollary of this proposition is that if you take two positive vectors pairs U alpha and B beta, which are non-zero, then U alpha is orthogonal to B beta if and only we get an order projection P, of course, other than identity and 0, and some positive numbers lambda and mu, so that U alpha is lambda P and V beta is mu times E minus P. We know what P is. P is precisely V half, where V is U divided by twice of norm U. Just follow this description and you get from here. And then use, of course, the characterization of orthogonal pairs. Fine.
Sorry, Professor. Karn, can you conclude, please? Can you conclude, please?
Oh, so, okay. I think.
Karn.
Okay, so I think I need entertainment. Oh, fine. So I think just quickly, let me tell you another interesting result that using this projections, we could introduce the spectral theory there. Is here, and then this is the spectral theory, and every element will have a spectral decomposition. And a spectral decomposition introduce the powers of V, and that introduces something called a binary operation here. And this binary operation becomes a bilinear binary operation in V infinity if and only by given underlying space, non-linear space V is a Hilbert space. So this is, I think I need to stop here. I got involved too much in there. Okay, thank you very much. I have to say a few more things, but okay, let's stop here. Thanks.
Thank you very much, Professor Karn, for this interesting talk. Are there any questions or comments? Yes, Professor Baslimans, you can interpret.
Okay, so yes, I was just wondering, going all the way back to the beginning of your talk, in general, if I don't necessarily see why you use a norm to start with to define your cone. One could just set this up in a general order unit space and try and define the spectrum of an element X as follows. So you have your order unit and you have your element, and suppose it's not a multiple of the order unit. Then I have a plane formed by X and this order unit U, and I see where it intersects. This plane intersects the boundary of the cone. Okay, and then I take as our basis vectors, I take those vectors, I normalize them so that they have order unit 1. And I just say the scalars I need to write X in terms of those two vectors in the boundary is actually the spectrum of X. And the absolute value of X is just the absolute values, taking the absolute values of the spectrum. Now, this is exactly what works in a strictly convex cone, that you get a nice spectral theory. And I think all your work is sort of in this setting, could be viewed in this way, in a natural way. And maybe, in fact, this is exactly the spectral theory in the spin factor that does it. So this would actually mesh perfectly with the spectral theory for spin factors. So did you ever think about this, of replacing this norm by just any order unit space and defining the absolute value of X in that way?
Okay, actually, I was looking for, I just said, I was just looking for certain examples of absolutely ordered spaces. And what I was believing, actually, that I should have said, what I was presuming that only C-star algebras or more generally JB algebras would give me the example. Then I obtained this example. Of course, it can be more general, it can be approached through some other methods, that's agreed. But see, my aim is, of course, this is part of the work. My aim is to understand the order structure in a C algebra or maybe in JB algebras, and this actually is a part of that. But I agree with you that this work is not that great, and then again this is a very elementary thing. Yes, I agree. Yeah.
Sorry, I'm not saying it's elementary. I'm just saying it might be interesting for you to actually look at the case where you take an order unit space where your cone is strictly convex and define the absolute value of x in the way I said. And then to do everything you do, it should go through in that way. And certain things will go wrong if the cone is not strictly convex, because your spectral decomposition is no longer unique. And then to get your later on, when you do your last bit, actually to get exactly a JB algebra structure, you need indeed to define the JB algebra product, you need to have some additional things. And that would indeed be interesting to understand what that is. I think I think it would be interesting to set it up in that way, rather than starting with a norm.
Actually, you're right. The only thing is, see, my looking at things is a little different from what you are saying. My interest is, see, a strict convexity of the norm gives me that absolute orthogonality. So what is the condition in the sense of order? Actually, see, my aim is to study the order theoretic aspect of C star algebras. So the strict convexity of the norm gave me this absolute orthogonality. And actually, I was not interested in spectral theory at all. I was looking at it, or I would say I'm still looking at it from the point of view of my order theoretic aspect, that how algebra appears. So what order theoretic aspect, without getting into the spectral theory. Spectral theory is algebraic notion. Without getting into it, how do I get that? Means what property of the modulus gives me that multiplication, which makes it say a Hilbert space, for example, in this case. That is my aim. But I agree with you that I could have taken a different approach had I have something else in my mind. But I had this approach in my mind, so I went this way. But yes, you are very right. Yes. Okay. Thank you.
Thank you. I'm finished.
So any other questions? So let us thank Professor Karn again for this nice talk.
Thank you very much.
And we don't have enough time for a break, donc